Hi everyone, I'm Alisa Cherniaeva. I'm a head of research at NIL Foundation, and today I wanted to tell you a story about how to prove sharding. And I wanted to start from short explanation what is actually sharding. Okay, here you see a picture, and you see a bunch of execution shard. When you think about execution shard, you can think about Ethereum blockchain, but with some extended functionality. So it's a little bit bigger. When execution shard generates a block, it sends block hash to the main shard. Main shard accumulated and publish a new block. And when SYN committee observe it, it starts prover network and it gets a proof. And when this proof got, it will send it to Ethereum site and it will be verified via Ethereum smart contract. So what we can understand together here, why it's not easy. Let's look at this part. How I said, each execution shard, it's a little bit bigger than Ethereum, and it can be a big number. So you generate proof for execution shard 1 and a lot of another proofs, and then you try to aggregate it. And only after that you can send it to Ethereum. And it's a complicated question in sense of hardware and how we can prove it. So if we wanted to make a goals for NIL Foundation, it will be how we can make aggregation step cheaper. And after we apply all changes exactly related to aggregation, we can think about how we can make prover faster. So it's our main priorities. Let's zoom into the SYN committee. How I told, SYN committee take a role of observer. It takes blocks from the main shard. And when task manager notice with new block, they distribute a task between placeholder prover. Each placeholder prover, it's a different server. And when they generate a proof, it sends a result to the SYN committee, and SYN committee will handle it somehow. Okay, and here I want to explain a little bit what's exactly placeholder prover. It's our proof system. It's Plonk style with custom gates, all of it, and it has several choices between, for example, commitment scheme. You can use, for example, KZG, or you can use LPC, but main part, and I think it's quite important part, because when you try to update a circuit, which will be written by another designer, it's hard. It's hard to understand what he tried to do. You spend a lot of time, and only then you will update it. So here we try to make design and circuit clear, easy updatable, understandable, and actually we already make a presentation about it yesterday at Protolayers Builder conference. It was presented by Alexei Shunsky. And yeah, it was good. Okay, and let's return to our system. We already understand what's exactly SYN committee, but we do not understand what exactly is prover network. We only understand what placeholder, it's just ZK prover. Here you can see different entities. Our usual prover, it's a ZK prover just. And we have a new entity, it's a master prover. You can combine and use master prover as usual prover, but with extended functionality, but you can run it separately. It doesn't matter. But for clarity, in this picture, I separated. Okay, let's for prover. We have input polynomials, and we should commit it and send it to the master prover. Master prover, in their turn, will generate a challenge. And usual provers should generate a linear combination from this challenge. And after then, master prover get all linear combination. It will run protocol, protocol for this picture, F plus G, and get a proof of proximity. The naive approach, it doesn't use a master prover, and it's just use usual provers. And it means what you will run protocol for each prover. And it will not be efficient, because in this approach, you will get less hashes. And if we're talking about hash-based proof system with LPC, it means that it will be pretty faster. Okay, now we understand a little bit prover network, how task manager can handle it. So just let's return to last slide. How you to see task manager just handle all communication between master prover and usual provers. And it's control server slot. Okay, now it doesn't understandable for us right now. What's exactly input polynomials? What is it? It's a scheme of EVM-related circuits, and I suppose most of you already know them because it's popular, designed by PSE team. And yeah, we a little bit regroup it and slightly improve it. So it's a little working in other way, but always naming should be familiar for you. But if you forgot or doesn't know, I just remind you. EVM. EVM control and prove all opcode sequence. Kichak, obviously for Kichak hash function. Merkle Patricia 3, read-write opcodes for all memory, stack, and storage operation. Bytecode, it's for separation each opcode from each other. And copy, for copy opcodes. You can see the same color here. And for example, you can see it in the Kichak circuit and bytecode circuit. It means that we have the same values inside Kichak and inside bytecode. And when we will provide aggregation step, we will check what it's exactly the same values in the Kichak and in the bytecode. So it's how our security hold. We actually prepared, especially for this conference, benchmark. We bought 2 Hetzner servers, the biggest one. We set up here placeholder with dynamic lookup constraints and defry commitment setup. Defry, it's let me return to here. This is called defry, distributed fry. Defry commitment setup. We take a node of our cluster and run it, and we push around 300 transactions to one block. Inside this transaction, we specially write a smart contract with different arithmetic operation, different read-write operation, just to check what everything is fine. For now, we think only about one shard. it's our first benchmark. And our results, it's for prover time, it's 7 minutes, 45 seconds, and RAM usage was about 40 gigabytes. And about RAM usage, it was actually good because in another benchmark for hash-based proof system, I always see much more. Okay. But we will not stop about it. And we have a future work here. It's Boil protocol. It actually was already presented at the last ZK Summit by Maxim Nikolaev. But I just make for you more high-level explanation how it's work. Let's think about just one round how it's work. Suppose we have proof P and polynomial F and accumulator big F from the previous round, and we get new proof P and new polynomial G. What we're gonna do with them? First of all, we have oracle batching. We take G, small f, and capital F, and we provide oracle batching protocol and get a new polynomial. For example, it can be just linear combination. And you can see from oracle batching, we have a line, and it will be a new accumulator, F prime. What we do with two proofs P, we make a circuit for verification of proof system and verify P old and P new and get a new P and new F. What's important to understand, how you see verification, two verification protocol and oracle batching. All of this, it's a circuit. We push it into proof system. We prove it before proof of proximity. We do not provide any exactly try step. We postpone it to the last step when we decide to stop and send it to the Ethereum. Maybe if it's not understandable, we can think about a prover which do everything except polynomial commitment scheme. It's not proper explanation, but for intuition, I think it's better. Okay, and when we want to apply it, let's return to our first slide with one. So it's an iterative operation. It means what it will work better if we have the same operation inside. We can accumulate, for example, only EVM circuits and then accumulate only read-write circuits, but the better way what we decide to do is accumulate whole block proof. So we get with different proof from execution shard 1, execution shard 2, and etc. And we start our boil protocol and get final proof. So since we do not make any proximity tests, it means what we have very small overhead. It's actually unlimited recursion. We can do it, and we do not need to restrict somehow our N. So for sharding, which we built inside new foundation, it will be the best choice. Okay, so this is how it works, and I hope in the next, I don't know which one, but in the next conference, I can bring a benchmark of boil protocol, and yeah. Let's return to our last slide. Yes, which is how it looks like. I don't know, maybe it wasn't a good explanation, but if you have any questions, you can go to just to our booth and ask about it, or ask it right now. Okay. Thank you for your attention. It was really nice to be here. I left here link to our research blog. And you can see here our post about DeFi. You can know all details. And we plan to publish here a post about Boil soon. I hope it will be in this week, maybe next week. And you can know not only about cryptographic research, you can know about our protocol research, who just try to build a sharding and some developers' notes. So thank you for your attention. It was really nice to be here. Do you have any questions?
Thank you, Alisa. We're definitely more than happy to have you at our next ZK Accelerate event to share more new progress with us.
Thank you.
Yeah, any questions for Alisa? Yes, please.
Hi, thanks for the talk. Just quickly, if you could go back to the DeFi. So here, the first prover uses powers of theta starting from 0, and then the second prover uses powers of theta starting from n. So is it necessary also for multiple provers? Yeah, I understand why we need theta to the power n, but that also means there should be some coordination between the provers on who is first and who is second, right?
Could you please repeat again last part? I don't understand.
So the question is, if you have multiple provers, does it also mean that each prover follows like a certain order because everyone uses different powers of theta?
Yeah. Yes, we actually have an order of provers, and it's not the centralized network.
Right. Okay. So there is some order of provers.
Yeah. We have order of provers, but it doesn't break any decentralized property because, how you can see, main part is just only cluster. How prover network will generate a proof? Because we can do it only on one prover node.
Right. Okay.
Alisa, I'm curious, do you have any plan to decentralize the network?
Yes, because it will be nice, just find a malicious prover and punish only him, not all prover network. But it's only in the plans, but I hope it will be for our next version of testnet. It will be in the spring, I think.
Nice, thank you. Thank you, Alisa.